In this video, we're going to talk about the concept of percent composition. In any given molecular formula, let's say something as simple as CH4O, we're going to have all of these different molecules. But the issue is we can't directly detect these molecules. It's really hard to say, hey, I just analyzed this substance, this gelatinous substance, and it's got one carbon, four hydrogens, and one oxygen. Hey, it's really difficult to figure that out. But what we can figure out is the percentage of the masses of these substances. And so percent composition of a compound becomes a pretty important thing in chemical analysis. We should be able to convert from a chemical formula to the percent composition of that formula. Now that percent composition is not going to be a molar percentage, it's going to be a mass percentage. So we could really say mass percent composition. So let's look at how we would figure that out for a compound like this. The first thing we need is the total molecular weight and the molecular weight of each of its constituent parts. So this carbon, that's going to have a molecular weight of 12. Hydrogen is going to be 1 apiece. Oxygen is going to be 16. So I can take the carbon, oxygen, and hydrogen, add them all together, and I'm going to get 32 grams per mole. That's going to be my total molecular weight. Now, if I want to figure out the percent composition of each of these, that's just going to be the ratio of that one thing's mass. So if I'm looking at carbon, it's going to be the 12 divided by 32, right? So I can total that out. And then for hydrogen, it's going to be the 1 times 4, there's 4 hydrogens there, divided by 32. And then for the oxygen, it's going to be 16 divided by 32. Now if I do all of those, I'm going to get 12 divided by 32 for carbon. So that gives me 0.375, so that's 37.5%. For the hydrogen, it's going to be 4 divided by 32, because there's 4 hydrogens. That's going to be 12.5%. And the oxygen, it's going to be 16 divided by 32. That gives me 50%. So now I can see the percent composition of this. Let's try another example. Let's say something like, let's do Na2SO4. Now I know each individual oxygen is going to be 16. Sodium and sulfur, I don't know those off the top of my head, so let's look those up. Sulfur is going to be 32. Sodium is going to be 23. Okay, and then I can figure out my total here. So I'm going to take 23 times 2 plus 32 plus 16 times 4. That gives me 142. So my total is 142. So now for each of these, for sodium, I'm going to take 23 times 2, because there's 2 sodiums, divided by 142. Then I'm going to take sulfur. It's going to be 32. There's only one of them, divided by 142. And oxygen. Oxygen is going to be 16, and there's going to be 4 of them, divided by 142. And that'll give me the percent composition of each one of these. 23 times 2 divided by 142 gives me 32%. We'll run that 32.4%. And sulfur is going to be 32 divided by 142. It's going to give me 22.5%. Then oxygen is going to be 16 times 4 divided by 142. That gives me 45%. So we've got all of our percentages here. Great. So now we also need to be able to do this the other way. If I'm given the percent composition of something, I should be able to figure out at the very least an empirical formula from that. That's going to be a little more challenging. Let's look at how to do that. So let's use this substance as our example. We want to build an empirical formula from this. All we have are the percentages of the masses. Well, the way we can do this is we can go, all right, so in a sample of a certain size, 52.14% of that mass is going to be due to carbon. So what size sample do I want to use? Let's just assume I've got a 100-gram sample. 100-gram sample, it's going to be the easiest sample to use because then what I'm really saying is I've got 52.14 grams of that being carbon. Great. So then in a 100-gram sample, 52.14 grams is carbon. Well, when I want to combine this into a formula, I need the moles of carbon. How many moles of carbon would be 52.14 grams? So all I need to do here is take the 52.14, multiply it by that molar mass. Getting rid of grams, going to moles, it's going to be 12. So 52.14 divided by 12. It's going to give me 4.345. Right. Okay, and then I'll do the same thing with the hydrogen. If I've got a 100-gram sample, then it's going to be 13.13 grams would be hydrogen. Then I can just multiply that by the molar mass of hydrogen. It's going to give me 13.13 moles. Okay. Next, oxygen. Again, that'll be 34.73 grams. Convert that into moles. It's going to be 16. It's going to be 2.17. And now what I'm really saying is all of these are going to have a consistent ratio. So at this point, what I need to do is divide by my smallest amount to get a ratio of 1 to whatever. So I've got 2.17 moles of oxygen. So I'm going to divide all of these values by 2.17. And I'm going to hope that that gives me whole numbers. If it doesn't, I'm just going to double it or triple it or whatever is going to get me to the smallest number of whole numbers. So let's take 2.17 divided by 2.17. Well, that's going to be 1. So oxygen is going to be 1. Hydrogen, we're going to take 13.13 divided by 2.17. That'll give us about 6. About 6. Great. And now for the carbon, we're going to take 4.345 divided by 2. Oh, that's not right. 4.345 divided by 2.17. That gives us 2. So our empirical formula is C2H6O1. Now we don't know if this is the molecular formula. We just know that this is the empirical formula. We could have this be C2H6O1, or this could also be C4H12O2, or anything else like that. So it could be C6H18O3. Those are all possibilities because all of these would have that same ratio and give that same percent mass, okay? So let's look at something. How would we figure out the actual molecular formula? Let's look at an example for that. Let's do 80% carbon, 20% hydrogen with a total molecular weight of 45 grams per mole. So we're going to do the same technique we just did. We're going to assume we have a 100-gram sample, which means that this is going to be 80 grams of carbon and 20 grams of hydrogen. And then we're going to take that and we're going to convert that into moles. So we take 80 times 1 over 12. It's going to go grams to moles. We're going to do the same thing with the hydrogen. We're going to go grams to moles. It's going to give us 1 to 1. And that'll give us 20 moles of hydrogen. And then 80 divided by 12. It's going to give us 6.67. And I'm just going to divide by that smallest number. So divided by 6.67, divided by 6.67. And when that happens, I'm going to get 1 carbon for every for every 3 hydrogens. So my empirical formula is CH3. Now what's going to be my actual molecular formula? Well, for this, I'm going to figure out What's the molecular weight of just my basic units? So this is going to be 12. This is going to be 1 apiece. So 12 plus 1 times 3 is going to be 15. So how many times does 15 go into 45? 45 divided by 15 is going to give me 3. So I'm going to multiply this whole thing by 3. So that means I'm going to get C3H9. And that will be my total molecular weight. That'll be my actual molecular formula. There we go.